Hey guys, how's it going? Welcome to another episode of Ferris Makes Hardware. This is our fourth episode already. This project is just flying along at a disturbingly quick pace, which is actually awesome. This has been super fun so far. By the way, sorry I'm not streaming other stuff during this time. I'm just like plowing through this stuff, and I would really like to get a lot of this out of my head so that I can kind of catch up on other projects a little more properly soon. Of course I do, G. Superlin. It's only fitting that I share the most up-to-date marketing material for the project. Honestly, I'm considering having this as like my background, just on my PC anyway. Anyway, a little bit of stuff that happened since last stream. I last streamed on Saturday. And on Saturday, I had a super long stream where we basically got stuff working. The CPU actually executed a series of about 4 instructions. It totally hacked it together, but it totally worked, and that was really, really cool. After that, I basically refactored everything on Monday just to sort of make sure the CPU sort of has more of the states you would expect in a CPU and start kind of factoring out the different kinds of coding and stuff. And I ended up just implementing a lot of the instructions as well because it ended up being really straightforward with the way that risc-v is encoded. So I'll talk a bit about that in a minute. The other thing that I did was, that was Monday. I think I made a lot of progress with just implementing a bunch of these instructions. If we look at the listing here, like basically all of this stuff and the shifts as well was just super natural to do because we already had an ALU. So a lot of it was just routing the data the right way and decoding things. And a lot of the decoding here is actually the same between these two sets of instructions. Same with the or and the and. Fences, I decided they're no ops right now because we don't have caches where these would really matter. E-call and e-break as well, I think I just did as either no ops or errors. I can't remember how I did these, but and then these control registers are really simple because like there's only a few read-only ones that you actually have to support, so you really only have to do the reading parts of all these and basically make them all the same. And also like you can get how many instructions have retired, and that's a super easy counter to implement. You can get how many cycles have happened since some point in time, and you can use that for both the cycles that you can get and also the time that you can get, as long as it's as long as you don't change your clock speed dynamically. So that's really easy. The branches were also super easy, a little bit more decoding than these because they didn't quite line up with all these more ALU focused instructions. And then these jump ones are really easy. I think the only one I actually had to do after Saturday was JLR. And then the last things were the loads in the stores, which I did on Tuesday and Wednesday, respectively. Particularly, I did the stores first and then the loads. And these were kind of a pain in the ass, mostly because in the spec I had read that you need to support misaligned instructions. I later realized, mainly because Per Vogensen told me on Twitter, that these do need to support misaligned access in the ISA, but you don't actually have to implement it in hardware. It's generally understood that misaligned accesses are going to be really, really slow depending on implementation. So you have naturally aligned loads and stores are guaranteed to execute atomically while the other ones aren't. And down here, it says we do not mandate atomicity for misaligned accesses, so simple implementations can just use a machine trap and a software handler to handle some or all misaligned accesses. So you actually don't have to do it in hardware. If you have misaligned accesses trigger a software trap, you can, I guess, use some of the whatever your trap mechanism is, you get some data to the handler that just says, okay, we tried to do this misaligned address with this data, just handle it in software. Which is a super good way to do that, actually, because then you can still have those available. But considering how much RAM a lot of these implementations will have access to, that extra software handler is going to be really, really simple. And then we get to make the hardware a lot simpler. This is pretty important because as I did the loads and stores, they actually got really really stupid. I'll show you my solution. I wrote them fairly quickly, and then I fixed them up a little bit, and then Per Vogensen also on Twitter. By the way, I'm totally doing this because Per Vogensen is awesome on Twitter. He provides me with a ton of insight for projects like this, so shout outs to him because I really appreciate that. And he saw that I posted this core because I posted the code and that it worked yesterday, and then just gave me a whole list of things to look through, and we're going to be looking at a lot of that today. A lot of those improvements. So I want to go over like the work that I've done so far and then how we're going to improve some of that. I think this will be a really fun stream. Anyway, I'm still probably going to support misaligned accesses in the hardware for now, just because that I don't know how I'm going to do traps yet. And just refactoring the code that's already there to make it fit, and then maybe we can remove it later, I think is kind of the best way forward. Let's get this. Also hacked anything on the MIF format? I did, actually. I did do that. I think I did that on Sunday. So down here, here's my ROM. Here's my ROM. So the ROM itself hasn't changed much, of course. It's just using different instructions, which we can do now because they're all implemented. Hooray. And then, of course, here's the MIF output. What I did in the make files, I just made this other tool called MIFT because I was really unhappy that I had to make it. And that's just a little Rust utility. So I just take the binary and run it through this MIFT tool, and then you get the MIF file out of that. So that's all I did. I just automated that. And then the tool itself, I put under this MISC directory. And here's MIFT. And it's just this. That's the whole code right there. And this literally just outputs a bunch of 32-bit words. It also does some sanity checks because we know the max size of the ROM here, and we know that it needs to be in 4-byte words and not be empty. And then it just hard codes everything, which is fine. This is the right kind of just thing to throw together for this. So thanks to 86 Tech. By the way, hi to guys in the chat. 8 Little Bits, SK Thess, Dark Second, Daniel Collin, G Superland, Studio C, 286 Tech, Miss Visser, Wister Tobe. Gang's all here. I have no idea why those other tools didn't work. The scripts that I tried just were crap, and I couldn't get anything to work with Intel Hex, so I mean, this is fine. Nice and easy. Does what we need it to do. Anyway, a couple things. This is this particular ROM file here. So what this is doing is this loads this address, which is going to be the basic, like the LED registers here, and then just loads this register with a known value and stores it into the LED register. And then this is just a loop of a bunch of misaligned writes, or it'll read it into another register, add a bunch, do a sub, and then write it back, and then just branch here. And it's not, the details there aren't too important, but we can see things like, let's see. Yeah, in this case, all these, here's the original write, and it's just one cycle, but then we have all these misaligned ones that are doing 2 cycles because it's 2 32-bit writes. So it totally works, but it's slower. And then the same thing works on hardware, and I should open up Quartus, because we are going to be looking at a lot of things in Quartus today. A lot of things that I need to fix here. That was it? That opened? Nope. Still working on it, I guess. Taking a minute to load. I don't know why. Hope this didn't crash. Hey, Pyro. Yeah, so there we go. This is, yeah, gonna do a couple things here. First of all, I just wanted to open up the signal tap thing, because it basically just shows the same thing on hardware. This is, of course, I didn't capture this just now. I can do that, though. Just capture a new one, even though it's gonna be basically the same. Bloop. Ooh, something happened here. Oh, I probably bounced on the reset button, actually, is what it looks like what happened here. Let me just do that again. There we go. Don't think so, Pyro. Don't think so. But yeah, it all works. This is actually a really long trace here. Just a lot of the writes. We can see the CPU stepping through its different states here. Loading 1, 2, 3 instructions, and then here's the write, and it goes down here and does a couple things. It's pretty cool. So I'm amazed that this is coming together this quickly, to be honest. Really thrilled about that. That's exactly it, Arthur Carlson. 90s stupid cool. It's very important. Esquites, the thing is about like video editing for those long streams, I have asked people if they wanted to do that, and just no one has responded. so I just don't provide that. The end. Anyway. So I want to talk a little bit about the implementation that I have here before we really dive into a lot of this stuff, because there's a couple really glaring issues here already that I want to talk about. At least I would provide both edited and non-edited, but I just don't. I'm not interested in doing the editing myself, and if no one else wants to do it, then oh well. Anyway. So this is the CPU. I think you guys have seen the ALU before. Nothing really changed here. I think I renamed a couple things, like I renamed the this to operator and left-hand side, right-hand side, and results. All of this is still combinational. It's not very complicated. And I generally think this is okay. It may not be. In fact, one of the things I want to start looking at here, we're going to look at the tools, and we're going to look at the netlist viewer. This netlist viewer will help us guide us through some of the things that are definitely wrong with this implementation that I'll talk about in a sec. But these are sort of the main things. We have the program ROM unit and then the XenoWing unit, which takes, is hooked up to that. This is kind of cool. We have the inverters for LEDs. Very simple. XenoWing itself is a little bit more complicated, but it's actually not that complicated still. Main thing here is we have the program ROM interface, which hooks up to the program ROM stuff. We have the memory mapper, the LED interface, and the CPU. Like the LED interface, super basic. Basically just a register. The program ROM interface, also super basic. A lot of pass-through stuff here that just talks to the actual program ROM bits that are bootstrapped outside of this. And then, yeah, clock for this data valid register just in order for this to interact with the bus properly. The memory mapper is also pretty basic. And you'll notice, of course, as I'm looking at these, just how simple these are. Keep that in mind, because that's not always going to be the case here today. So the CPU. We're going to wait a second. Whoa. This is bad. This is not how it's supposed to be, guys. It totally works. Let me say that. This totally works. It is functionally correct. To my knowledge, there are probably bugs in here, but this is just stupid. And I think I know why for a lot of it. So we're gonna fix things that I know are wrong, that I know I just designed poorly, and we're gonna watch this thing shrink to some degree. I mean, it will still be somewhat complicated, but it's not. I don't think it's gonna be nearly this complicated. That's exactly what this is. Mux is all the way down. Basically, what this tells me, and again, I could be wrong about this, but what this tells me is that when I compile this to a netlist, the way I did a couple things, it just gave up and just, okay, you asked for this. I'm not going to try and find a pattern. I'm just going to blow up. Again, this totally works. It's just, I think this is indicative of a bad design. So it's fun to look at this, though, and it's important as well to get in the habit of looking into this, I think, and So yeah. This is not what peak performance looks like, let me tell you. I am not getting peak performance out of this. And there's a couple things here that aren't too bad. I think this is the main state thing here. Here's the ALU. Way down in here. And the ALU, look at how nice the ALU looks. Like there's a lot of things here because it's basically doing all of the operations for all of the bits. But this still looks really nice. I think this is how our ALU basically should look. And of course, a lot of these are thick because I think they're, a couple buses, but generally this is pretty good. So why doesn't our CPU look like this? Oh, I clicked back. This will take a minute. I'm going to tell you something that really bugs me about this huge net list and why I scrolled through it like that. I didn't just want to show you guys that it was huge because you could see that from the bird's eye view. I'm actually trying to find one of the hardware units that I put in there, and I can't find it. There's a reason why I want to look at it on its own, which I'll get to when I talk about why I think this is the way it is. Oh, it's nowhere near that high, G Superland. I'm still running this at, I think right now I'm running it at 50 megahertz, and it's not even a problem, but it is bad. And there are several reasons why, and I would love to talk about all of them, but we're waiting. So, I mean, practically speaking, I could just not care about this, but because Per Vogensen gave me some very clear things to try, I'm actually very interested to see how this responds. And the main thing is that, so with a CPU like this, like I designed it, out of the gate to not be the best CPU, right? I just designed it to be something that I could understand at the Verilog level. And I think right now I have that. But if I can do things that simplify this netlist and simplify the code, I'm totally interested. If I can do things that just simplify the netlist, I'm somewhat interested. And if I can do things that are just going to improve performance at the cost of complexity on both levels, I'm not interested yet. I probably will be later, but right now it's most important that this works and that I can fix bugs in it. And then it's important that it's not insane. And I don't think this is actually insane. Like, I think it's excessive, but I don't think it's insane. So I think it's just, I really want to find, so I have a unit in here. It's called the read buffer. And I'll get into what that is in a sec, but I just want to find it on here. It's what bugs me. I just don't know where it is. Maybe it's here. There it is. Nice. It's right here. Right next to my instructions read and cycle counters. So my read buffer, here's the interesting thing. This read buffer really is not more complicated than the ALU. But still, look how complicated this looks. Like, this still fans out quite a lot more than it should. This is basically a 32-bit element FIFO. It's not even a FIFO. It just reads in 2 elements, and then you can just look at the data. And this already fans out a lot, and this is indicative of a pattern that I used in both this and the registers of the actual CPU, which I think is causing everything to blow up like this, first and foremost. But yeah. 286, I think it's some of that. I think there are some obvious mistakes that would still allow me to do that, but yeah. It's not an ideal implementation. I never meant it to be, but still, there are some things here that are more wrong than just that, I think. So yeah. So let's actually look at some of the CPU here. Not much has changed here. We have this same interface with the ready address, write enable, byte enable, read request, write request, read data valid. The same interface that we always had. And then the clock and reset. Some registers for controlling that. There's a program counter, 32 bits. I have a bunch of registers. There's 30 of them. Actually, 31 of them. They're all 32 bits. I have 64-bit cycle and instructions retired counters, which are just used for those system functions. We have a bunch of states here. So we have an initial instruction fetch setup, and I'm probably going to rename this to just like wait until the rest of the stuff is initialized state, because that's really what this is going to be. I kind of put this in there when folding a couple things into other states, and I'll get to why I did that. But this will basically just be a wait until the DRAM is initialized state. Although I probably actually don't need to do that because just looking at ready might be enough. But anyway. There's an error state, and then there's the main states of the processor. So it is still one big state machine minus a couple other things that I've pulled out, and there's some more that I will pull out into more parallel units. But the main state machine has an instruction fetch cycle, or maybe more cycles, but it has that state. It has an instruction decode state where it basically just takes the instruction bits and looks at them and chooses, how things are hooked up. Then we have 3 memload states. Because loads it's going to dispatch 2 loads, or up to 2 loads, 1 or 2, and then it's going to wait until the result comes back before it moves on. Finally, we have 2 store states because it's going to do up to 2 stores depending on whether the alignment is correct. We don't need to wait for anything to come back. We just need to know that those go through. So we have 2 states for that, and then we have a write back state, which will pull in the results from mostly the decode state, but also the mem states, the mem load states if applicable, and then write those back into the registers. So not that terribly difficult. I mean, again, if you were to do this a little more properly, you could separate these into separate functional units, and there are some of that I want to separate out. But then the problem there is that a lot of like the enable and disable lines on those and stuff, I think, get kind of complex, particularly with detecting hazards and dealing with those. So I think basically I've avoided that by doing this. And then we have, registers and wires for hooking up the ALU. We have this read buffer again, and the read buffer is basically so that we can just dispatch, like when we do a load, we can basically just dispatch the loads right away, and then we just wait until our read buffer, which again is just a 2-element buffer for 32-bit values. When that, fills up, has either 1 or 2, depending on how many we dispatch, then we can continue. So like the wait state for the loads just waits on this count to be what we expected, and then pulls in the data. And we'll come back to this because there's a test I want to do on this that basically has to do with the way that I'm doing these arrays that I think is wrong. So we have that. There's an instruction register, which is basically the output of this instruction fetch thing and what we use on the decode and a lot of the other decoding signals in the other states. And then I fan out this instruction thing to basically all of these signals. These signals are basically just nets. It's just named values that are just naming different kinds of combinational output from this instruction register. So while they look like registers, they won't end up being registers just because we only assign to these here, and they only change when instruction changes. So these are just like taking different bits and giving names to these values. These -1s here and a couple other things might be really shit, so we'll probably have to fix those. But generally, a lot of this is just fine. Like, this is kind of how you would want to have this. Anyway, here we wire up the ALU to the control registers that we have, like the op, left-hand, right-hand side, and then we get the result out of that. Here's our read buffer again. It's mostly just hooking that up to our, read data and read data valid signals from our memory interface. And then here we can pull out the data and the count from that so that we can actually read that stuff and make sure that's operating how it expects. There's also a clear signal that we can give to that when we're going to start a read. We send clear to this, and then we send out the reads, and then we wait until both of the reads have come back into this unit. So there's already kind of a separated out unit. What that allows us to do, by the way, is when we issue reads, let me find an example here. I think this is a good example. This is a misaligned read here, I think. No, that's a write. Look for our read request, because we should have, I want to look at read and data valid. Yeah, so here we issue a read. It's a misaligned read, so we actually issue 2 reads. And as we're issuing the second one, the first one actually already comes back. So that's why I separated this unit so that this could come back while we're doing this other logic. So that kind of allows us to separate that easily. So that's why we do that. And then that's about it. So we have sort of two main parts of our logic again. We have the clocked part, which is basically just going to handle either the reset case or the normal update case, which is basically we're just feeding new values into all these registers. And the new values, that's where all the magic happens. So we have this big combinational block. A lot of this is written in a pretty procedural style. We set up some initial values, which is just the original register values, like next cycle counter and stuff. And then it gets pretty simple. So in the initial instruction fetch, it sets up, the state for the initial instruction fetch. We don't put this in the instruction fetch state because we want to have the instruction fetch set up so that when the state comes and we get the value back, then we're going to, finish asserting the read. Or actually here, we wait until the memory interface has seen the read. And then when it gives us the data back, then we can move on to the next state and pull in the instruction into that register. So that's pretty straightforward. Then we get to the instruction decode, and a lot of this is just decoding some stuff. Like what is the next ALU op going to be? Well, we can look at this particular part of this this instruction and just decode these based on what that instruction listing was in the spec. So this just basically becomes a mux, and then we have sort of these default left-hand side and right-hand side values, and then this case stuff. So all this again becomes a pretty simple mux. I think generally the decode here is actually pretty good, just in terms of how this logic looks and what it ends up becoming. So I'm not too concerned about this because it's mostly just like it's doing what a decode state should, I think. So that just basically sets up everything into the ALU and sets up what the next state is going to be. If it is going to be a load or store, it'll go into these either load or store states, and then we use the ALU to calculate the offset. Otherwise, it's going to go into the write back state already, so we can just skip those altogether if we don't actually need to do them. The loads and the stores are actually set up into two stages each, again because we can dispatch more than one load or more than one store. This is something I actually think we can improve on. We'll get to why, but basically we have the loads, and like we have load byte, load half word, and load word. And here I dispatch on different next states depending on the alignment cases. For the byte enable stuff, I've already done this with a nice shift here, which again will become a mux. This is only like 4 different values or something. So I've simplified the logic there, but I haven't really simplified the next state logic here, and I definitely can simplify that. Another thing that was pointed out to me is that the loads here, when the memory, well, we'll get to that in the write back, but they're actually wrong. I mixed up a couple of things when I wrote that, so we'll fix that really quick. But anyway, load 2 again just loads from the next address and then sets the different byte enables for dispatching that load. Then it's going to wait until we get the load back from the buffer, which it may not have to do depending on the different states here. And again, a lot of this can be collapsed and simplified, so there's just a bit too much logic here. Like I wrote it kind of in a copy-paste style just to kind of see how it would look, and now that it's all fanned out, I'm starting to see the patterns. So we're going to be able to simplify a lot of this. And the store is basically just the opposite of that. We have the same store byte. It's either going to, depending on its alignment, it's either going to, it's going to have these 4 cases, because we're going to take the top 30 bits, and that becomes our 4-byte aligned address, and then the bottom 2 bits are going to determine what our write data looks like. So it's basically just these with padding. So again, these can be simplified with shifts, so that should be relatively easy. And the same sort of stuff. The second store as well is the same kind of thing. So, I mean, this stuff really ballooned more than I expected, which is why a lot of implementations don't support this in hardware, but also at the same time, we can support this better. And then once we've dispatched the reads or the writes, we're going to get to the write back state. And then here we just, again, wait for any data to come back, or wait for our, sending any data to be done sending. So 286 Tech, I actually could do some of that comparison because I think we can at least see how many logic elements there are. Of course, that's logic elements including the signal tap stuff, but I also could remove that just to write down that number. So I think we should actually do that. That would be good. But yeah, here again in write back, we just sort of have different muxes again, just based on which instruction we had, and that determines where things are going to be written. There are a couple major problems here, though. First of all, I'll get to this first problem with these loads. So load byte and load byte unsigned, I totally mixed these up. So the unsigned ones are totally doing sign extends, and the signed ones are totally doing 0 extends. So I'm going to fix that first because that's just trivial and totally wrong the way I did it first. So that's fine. Now it should work. Tomix, thanks for the sub. This number notation, this is this many bits, and then like the format specifier for the value, and then the value. So that's what that means. So this is 16 0 bits, for example, and this is 16 times this bit, or like this bit here 16 times is what that is. Again, a lot of this logic can be simplified, and it should be. You'll also see there's a lot of this RD -1 here, and having these subtracts in a critical path like this is really bad. And again, that mostly came from copy paste, but we really should only have that in one place because that is going to be, if it's basically a barrel ladder with -1, it's going to be a long path, as well as it's just bad to have this repeated all over the place. But we're going to fix that in conjunction with fixing something else, which I'll get to in a sec. Mostly it's pretty simple, though. Also, this happens in a lot of places, though, with this RD stuff. But, I mean, the logic isn't that terribly complicated, really. Then again, the system ones are really simple because it just, reads these out of these different instruction things depending on which system register you ask for. And finally, we set up the next instruction fetch at the end of this state. And we just say, if our PC is not aligned, which it is actually guaranteed to do that, to be aligned for an instruction. So we'll just go to the error state if it's misaligned. Otherwise, we'll set it up. That's mostly for my own debugging. So dark second, that's part of it. We'll get to why that matters rather than just saying it. But yeah, that is absolutely what we're going to do. But there's a little more than just this being verbose that we need to fix by doing that. So I want to talk about that as well. Anyway, that's it. Like, that's the whole logic here. Everything else is just details about like where we get the bits from based on the encoding of the actual ISA. And yeah, so I think this is overall, pretty simple. I think it's like 600 lines of code, 630, plus of course the read buffer and the ALU. But generally it's not too bad. So it's a good starting point for something that we can, first of all, it's basically usable already as is, but it's a good thing to just spend a little bit of time improving and then forgetting about for a while we work on the rest of the system. Before I get any farther, I want to commit this fix. Whoops. Oh, I hate when I do that. Hate when I end a commit message with a exclamation point like this. Is really annoying. Let's do that. So yeah, that should be fixed. So that's one thing down. That's one thing down. The next thing I want to look at, though, is the way that I've done these registers, because it's also a same pattern that I've done in this read buffer in the way I handle these arrays here, and I think that's why a lot of this is just fanning out like crazy. So I think there's a pattern here that I'm using that isn't simulating or isn't compiling how I would like. Really quick, Daniel Collins says, have you made any rough plans for the GPU? Yeah, I want to do some basic kind of rasterizer. I'm going to do it in the CPU first. So I'm going to make like a MMIO kind of display unit, or sorry, a DMA kind of display unit that's just going to pull pixels out and send them to the HDMI. And then I'm just going to do it as software first. But yeah. Mr. Anderson, how does risc-v spec deal with exceptions? Are they required or optional? From what I could tell in the spec, they are totally optional. So right now I haven't done any of that. And I probably won't for a while because I know that, for example, with synchronizing with the video hardware I want to do, we're not going to need it. For synchronizing with the controller hardware I want to do, we're not going to need it. I do want to have an internal timer, though, because that will allow some CPU-controlled sound sample playback, and I might want to have it for that. And if I have it for that, of course, I'll implement it for the GPU and stuff too. But for right now, I'm kind of trying to defer that decision because as far as I can tell, you don't need to support that. Which is also why I'm still going to support unaligned loads and stores in the hardware, because if I have exceptions, then I can also use that to implement traps and then fix all that in software too. But I'm just going to not do that for now. I think it's a shorter path to not have them for now. But yeah, from what I can tell in the spec, they're not required. And there's no spec for doing that. I think the audio stuff will be really fun. I mean, I think it's all going to be pretty interesting, but yeah. Anyway, so one of the things I do here, generally the style that I'm writing a lot of this in is called a two-process style. And so I have a lot of this, like, here's a value and here's what the next value for that's going to be. And it's a really, it looks like a really stupid way to write this stuff. But if I rename this next to combinational, it might make more sense. It's basically, let me paint this up. Yeah, okay. So this is a register. His name is Bob. No, his name is register. Reggie. We'll call him Reggie. Here you have a little clock. You have an input and an output. You often call this D, and you'll call this Q. Not that important, but it helps. That's awesome, 286 Tech. Yeah, it's not a proper stream without paint. I could totally get like a tablet at least, but I don't want to. I like having these drawings not be very good. I don't know why, but I do. So the way a lot of these registers work is ignoring some timing constraints. So we're going to ignore those. The input is going to have some value on it, but the output isn't going to be affected. So the output, let's say this is a 1-bit register. So the output is going to be either 0 or 1, right? Like, just assume that. And whatever the input is, it doesn't matter. The output is still going to hold its value. But at some point, a clock signal comes in. So in this case, when the clock goes from like a low to high on that kind of transition, like this is what we call the positive edge of the clock. There's also the negative edge, but we only care about positive edges. So every time a positive edge of the clock happens, the input gets reflected on the output. And then what happens is it just holds that again until the next clock happens, right? So in order to change the value of this, we need to feed some kind of value onto the input. And have that be stable when the clock comes. So a lot of this ends up just being like feedback networks. So if you want to have the value of this register just flip on every value of the clock, so you want it to be like 0 and then it'll go to 1, and then on the next edge of the clock it'll go to 0 again. The way to do that is just stick an inverter here, for example, and then just route it back to the input. And this would give you, this would give you exactly that behavior. So whenever the output would change, the input would just be opposite of that, and then when the next clock hits, that input is now reflected on the output, and the whole thing repeats. So that's kind of this is enough to sort of illustrate the mental model we're working with here. If I just undo some of this, that NOT gate that I drew here, if you can replace that with, we're gonna have a little cloud here, and this we're gonna call this combinational something, and then back in here. So if you look at this, if you go by the names that I have in the code, it's basically Reggie. If you saw Reggie, it kind of refers to this. This is Reggie. And then if we tapped off the value here, whatever that would be, this would be Reggie underscore next. So whenever you see my RTL code that writes this, basically think of Reggie as the actual value that the register has in it and what's coming out of the register, and then the next value is what comes after the combinational logic here before this comes back in. So if you look at some of this code, like the read buffer is a little bit simpler to look at this. We have But okay. So we have this flip-flop stuff, and you can see it's reactive to the positive edge of the clock. It's also reactive to the negative edge of the reset. I'm going to hand wave that for now because I think that's actually a bad idea, but I'm going to fix the code later. We have the reset condition because there's also a reset here, which is the reset active low. I think you read it like that. Anyway, not that important. But if it's reset, we're going to reset this stuff to default values. Otherwise, we're going to load it in with the next values, which is basically this describes this left section here. So this is the FF stuff. And then this always calm block is this stuff. I want to capture this stuff here. Glad you guys are having fun. But yeah, so that's kind of I think that's enough to describe basically what's going on here and why the code is written the way it is. It just makes it a little simpler. So we have this part that's basically routing the stuff for the flip-flops and when the flip-flops change value. And then we have this stuff which describes the output logic of this blob. And so initially, like data next and count next are just going to be the value of whatever those registers are. But then here we overwrite them based on these conditionals. Now, if you're actually going, so this is a little bit misleading because it looks like this is going to run sequentially. It actually isn't. It's going to sort of act like it is. Basically, all this stuff becomes priority encoders. So we can sort of break this down and rewrite this, which I kind of want to do just because I think this will be kind of a cool way to describe a lot of this. Basically, if we have, let's see how we can sort of compile this by hand. Yeah, this is why I don't record the chat. So we can sort of fold these things here into something like this. We can say if clear and turn this into a ternary expression, and then we have this, right? So that's basically equivalent, and that's what this style means. It means we can sort of write it in a procedural style, but this is really what's going on here. And you can very, very easily imagine how this becomes a mux. You have this as the one input to the mux, this is the other, and this is the selector, and then the output of the mux is going to be tapped here. So the mux is inside this cloud, basically. And then we can go one step further. So the read data valid here, for example, we do the same thing here. So we look at both of these, the data and the count. So the data is like this. So if read data valid, data next count is going to be this. And there's some things here that I think I'm doing wrong, but then it's going to be some stuff. Actually, that goes here. Some stuff. Otherwise, it's going to be the previous value of data. Again, we'll get to the count stuff here. Yeah, falls apart there, and that's also why I think the netlist is blowing up. But anyway, this same thing also happens. So there's this, but then this thing takes precedence, so this becomes this, basically. Read data valid. It's either going to be this, like this, right? And again, it's very easy to see how, again, other than the stuff I hand-waved here, it's easy to see how this can be described in hardware as sort of a continuous, just set of gates that just represent this continuous logic. But because of the way that this combinational stuff and these blocking assignments is what they're called work, we're able to write them in a way that's a little more natural for describing the logic and the priority of the logic, at least more natural for me, for example, but we'll still get this on the output. This would be a perfectly valid way to write this, by the way. In fact, in Verilog, all we would have to do is we would do assign here. And this is exactly the same stuff we would get. And if we look in, for example, the CPU, this is exactly what I do when I fan out all of this logic from the instruction register. And again, you can see, I think this is pretty demonstrative of how this stuff really works and how this stuff is encoded. Of course, you also have a lot of things that run on this like any other compiler would, like a lot of dead code elimination and those kind of things that you would expect. But basically, this is a pretty complete picture of how this logic is actually working. Now, the part that I hand-waved away is the part that's when Per Vogensen, again, I'm mentioning him because he's sort of the impetus for doing this today. One of the things he pointed out is that he doesn't think that the way I did this would actually work with those array values. And I think he's actually right, because as you can see here, I basically was like, I don't know how this works. So it's probably true that all of this just gets really messed up. Yeah, I think that's also kind of why it's important to talk about this 286 tech, is that, again, that is not, when you see this code like this and this combinational stuff that looks sequential, it isn't actually sequential. It's just another way that you can describe, like it's sort of an inverted way to have the logic to what it's actually going to be. And I actually think this model is relatively simple, and I think it's actually complete enough to describe most of what we're doing in terms of just updating the digital parts. So I think this is really helpful. But yeah, so the thing that I think is a problem here, and we're gonna look at the read buffer first because it kind of fanned out a lot more than we would have liked, and I think also this crazy fan out is also because the compiler is not understanding what I'm trying to describe here. So that model that I point out, this works really well for like individual registers. So for example, if in the CPU, like this instruction one, it works really well for this, because if we look at the instruction becomes, Reggie here, and instruction next becomes the input to Reggie on the next cycle. So instruction itself, as you can see here, just gets updated with instruction next whenever there's a clock tick. And the logic for instruction next, this is only touched a couple places. So initially, it's either whatever the current value of instruction is, or if we're in the instruction fetch state and ready and read data are valid, then it's going to be read data. So we can, again, rewrite this like this. Or we can say ready and read data valid and state is state instruction fetch. Then it's going to be the read data, otherwise the value of instruction. So again, that's the combinational logic that instruction next gets. And this is fine. This is a very simple piece of logic. So this is just fine. It works. The point I'm trying to make here is that this model works really well for like individual registers. When you have arrays like this, though, like what we have for the different read buffer values, so we have an array here where it's basically do I have 4 of these? That seems a bit wrong. I'll definitely have to check that out, 286 Tech. The whole zip CPU blog is really good. Yeah, first of all, I think this data is not right, because this should only have 2 of these. First of all, I should only have 2 of these because I only need 2 slots here. And I think you get that from this. And then the count here, I just use the bottom 2. I want another bit on the count, by the way. Yeah, we'll just do that. I want another bit on the count because I want the count to represent like 0 and 2 should actually be different states according to the count. But I think this makes sense here. This buffer is only ever going to be 2 elements large, so I don't really care that that's, that simple. I'm going to recompile that really quick, by the way. I don't think this really helps us that much. I should be able to make test. Oh yeah, we need to bubble those changes up a little bit here. Here. Yeah, and that seemed to be the same. In fact, if I go here and just reload this, it should be fine. Yeah, so that's fine. That just removes some redundancy here. But yeah, so it's exactly what 286 Tech is saying here. Like, when we work with those single registers, we basically are updating these same values every cycle, and that's fine because that works well for those initial registers. But for cases like this where you have this array of data, you can think of this as 2 registers, and it updates the data for those every time, which is not necessarily terrible for these 2 registers, but we really only need to output 1 at a time ever. So we're going to have to rewrite that. And I think that the compiler here in Quartus is not understanding that very well. So it is just fanning out all of those assignments. And I think that's why our netlist totally blows up like that. So so yeah, that's exactly it. 286 tech. We're gonna remove some of these muxes that aren't going to actually be used every cycle. I think there's a lot of parts of the design that could be improved just by sort of refactoring a lot of that, but a lot of it doesn't need to be, but definitely these registers I think is fanning out a lot more than it has to. So that's definitely something that we'll want to fix. So let me check something really quick. I think I'm also I'm just going to commit this really quick just to have it separate from the changes that we're going to make. And the other thing that I want to do here, I actually want to recompile this. Because that should actually simplify things a little bit just for that. This takes a minute. Actually takes a couple minutes. In fact, I'm going to be right back, actually. And I'm back, and it's finished. So if we go back into this netlist viewer, here, I think I might even be able to go in here. Just see if I can just go into the instance here. Just go into this read buffer. Okay, yeah, I found it here. So this still found out more or less how it did before, which I'm not that surprised about. But yeah, there's basically a lot of muxes here because it's updating all of the bits for all of those registers all the time. Or really, we should only update the bits of this little buffer that are actually being written to within the cycles that it's actually being written to. Otherwise, just leave the registers alone is more or less what we should be doing. So I think the fixing that in this particular context is going to be easier first. If we can figure out the pattern here for this read buffer, and then apply that to the registers, I think that's what the right way to do this is. Because then we can sort of see and compare these two things in isolation before we move on. By the way, before we do this, now again, remember this is still with signal tap on, which means we're going to have some extra logic elements in our netlist. And I think that's fine just to take this measurement because it's not going to be that terribly important that we're super accurate here. But I just want to write this number down here. This is 7797 LEs. We had 4503 registers. And then we had a lot of memory bits. Most of this is going to be taken up by the signal tap thing. So I think that's good enough just to have like some numbers before we start making a lot of these changes. Good enough. We'll do this. Not too bad at all. And also, based on the resources available on my FPGA, this is also not a terrible number for the CPU and the memory mapping and everything because, you know, I have 50,000 elements, so we're quite all right with this. And I think the memory interface was another 6. And yeah, it's not too bad. Yeah, memory bits is how much block RAM we're using. A lot of this, again, is signal tap because that's where it actually stores the data that it taps off the signals first before sending it back over JTAG. So a lot of bits there. There's also 64K kilobytes of memory that we're using for the ROM. Even though we don't use all of that, I have it allocated already just so I can work with it and it's not a surprise later. So yeah. Anyway, I had a note here about how to do this. So I just need to find it. Yeah, okay. So, if we look at our read buffer, it's this data thing here that's important. And instead of doing data next, I don't think we're going to do that. We're going to do something like this. I think we want something like data write enable. that's all we need because we already have the address. And we can do logic 31 down to 0, data writes. Although we may not even have to have this in a register here. Disused, I think the answer to that is yes. Here, though, we do want a logic data write enable next. I think we do still want to have that same pattern there. Data write enable. Next is data write enable. So then if read data valid is this, we're going to still update the count as we did before. And we're going to do data write enable next is 1. Fact, do this. Instead of doing data and data next here, we should rather do something like this. Actually, we'll do that. We'll get to this as well. Yeah, I'm not sure we need this actually, because I think what we can do something like this, where we do if data write enable and here's, or we may not need this either. Okay, here's an issue that I'm having with this style is when you start mixing these, I'm not liking it too much. But I guess I'll just have to sit here and play with this until I think this makes sense in my head. But it's basically going to be this. If data write is enabled, then data count or count next, really. We're going to assign that to the, we're going to assign the read data to this. I think that's basically what we get. Now I'm just going to try to compile that really quick here. No warnings in those bits of the code, and it seems to work. Nothing is different here. And ultimately, we want to check this logic here. I need to rebuild this. Refresh just give me that, or do I need to actually build this again to do that? I don't actually know. Now, what actually confuses me a little here is I'm not entirely sure how this is going to end up being different when it gets synthesized. I think we've updated, but I think we need to recompile this for that to take shape. Just do that. Oh, so this should really be count, shouldn't it? Yeah, I would imagine just running this here, this analysis and synthesis, would be enough. I would imagine. I just want to see if this gives us... I don't think this gives us any warnings about this. It does actually give us one warning that I'm going to fix really quick. Which is, again, this. We just want that bit of this. I think we're good there. Yeah, nothing in there at least. Then we'll do this part here. Yeah, it makes sense that we would have to do this again to see the net list. So I guess what I wouldn't understand is how, like, I would imagine this still to get kind of inverted how the other thing was. Maybe this actually gates the clock or something. Based on this count logic. Like if these are sort of, I guess they could just be enable lines too to these registers. So they'd still get the clock, but they would only get enable ticks whenever this was the case. And then read data, for example, is actually routed to both, but then count only if this bit of the count only affects the enable bits for the different elements in this array. If that were the case, then I could understand where this would definitely give us what we want instead. Whoops. I double clicked on clear. I don't think that's going to help us much. Maybe it does. Yeah, no. Yeah, this still doesn't change much in this case. And maybe that's fine. Maybe that is all we get here for this particular part of this design. Because at least the indexing here, as opposed to in the rest of the CPU for all those registers, is a lot simpler. So It might just be that this is what we're stuck with. Because, yeah, as 286 Tech mentions, logically, this is still basically going to be the same. In terms of being able to access both of these from here, and the inputs to data, when this is not the case, still ends up being muxed with whatever the previous data was. Again, we don't really run into like timing issues here or anything because we're only working with assigning, you know, values to these registers. And so I think the logic here is safe. But it didn't really help us much in this case. Well, we'll leave this for now, though. We'll see if this kind of thing helps us in the CPU, which I suspect it will there. Best time, Reth, if I'm reading that right. Thanks for the follow. So I think we'll just try this in the CPU now. So I think the easiest way to do this, there's a couple things we want to do here first, by the way. And one of these is that we're actually going to take this register thing, and I'm actually going to keep the same amount of registers here, but I'm going to make this 31. And what this will allow us to do is now we're still going to have register 0, and its initial value is still going to be 0. But instead of having all this -1 crap here for like RS2 and RS1, that just allows us to get rid of all that at the cost of having, you know, another one of these registers, but I think that's going to be fine. What I was hoping when I wrote this is that the compiler would be smart enough to know when a lot of these subtractions actually need to take place, and I would imagine a lot of those paths would be collapsed, but I'm not actually convinced that they are. And either way, of course, this simplifies a lot more of the code. Of course, we're still going to want to get rid of these already is not equal to 0 parts later, and we'll get rid of that when we sort of collapse the writing. But I think that already might help. By the way, really quick, I could also check if these elements actually changed. That seems to have increased. I wonder actually if like the place and route stuff just does more optimization. It very well might. So maybe that's bogus. Yeah, I guess these wouldn't have to start at 0. Of course, then I don't know how a lot of these indexing would work since RD could still be 0. It wouldn't be on any of the cases where you actually hit those code paths, but yeah. I don't really mind having an explicit 0 register in here. Just that those RDs need to be flattened. So we can start with that at least. I'll do it again in our simulator. It's a lot faster, which is why we set up this whole setup here. So I'm just looking for any things that it gives us. So of course we still get these case incomplete warnings, and that's just telling us that I have a couple of cases that don't cover all cases, and that's because it does some like decoding stuff on different states of the processor. So it's fine that it doesn't cover all the cases, because like by the time we get like a write back, for example, we know a lot of other things can't have happened. So oh yeah, that probably might make sense, 286 Tech. But I think I do want to go 0 to 31 here. Keeps it keeps it relatively simple. I'm going to run this again. I don't expect. Well, it would probably help a lot in terms of removing all these subtractions if they ended up being elaborated such that they couldn't be collapsed, which is quite possible. Right now, writes to R0 are handled all over. Basically, on all these writebacks, all of these right now have checks that they only do the writeback if RD is not 0. So it happens in the process. So we're still safe, even though if we just have that now. I've just removed the offset codes here, or the code to offset this value whenever it writes. But it still does all these checks to see if it's not 0. And we should be able to remove a lot of these, because I think like when you have an if like this, all the stuff you touch in here that you're assigning to, in this case it's state next and regs next, all of those, this actually ends up being part of the expression that determines their next value in everything that you write to in here. So even just removing a lot of these will just simplify a lot of the logic solely for the purpose of not having to do a lot of these checks. In the spec, you are allowed to write it. In the spec, you're allowed to write to R0. And in fact, a lot of things do. I think like no-op, for example, adds 0 to 0 and stores in 0. Or I think it's I don't know if they do it as a register add or register immediate, but yeah. So you're definitely allowed to write to R0. Again, here I don't think anything changed. If I refresh this, we actually should see a couple changes, not in the overall timing, but in the registers that I have written here, because now we actually have reg0 available here, because it basically offset all the register values here. But none of the behavioral stuff should have changed. And our netlist viewer here is not going to get much prettier. Our logic elements I don't think really changed much here already. Again, the CPU is going to be a monster. That seemed a little faster. In fact, it actually looks a lot simpler just doing that. Actually, this is actually remarkably simpler just doing that change. I'm actually surprised. Don't you guys agree? I mean, I'm purely going off of what I feel like I remember this looking like before, but this definitely looks smaller to me. In fact, I can compare. I'm just doing a little screenshot test here. Because why not, right? I wonder if there's a way to get, like, if I just right click on here or something. I would love for there to be like a way to see how much stuff there is here. It totally loaded faster, and I'm pretty sure this looks simpler. I am actually just going to compare screenshots here, because I think that's enough to see if it was like definitively simpler or not. So I'm just going to get status. We're going to do a Git stash. And I'm just going to run this compilation again. And I'm not that surprised about that, actually, because, again, looking at this logic, like, I think the stuff with the loads and stores can be simplified, and the stuff for the register writes can be simplified, but it must have just had a ton of these different subtractors elaborated in the hardware just because of that. So removing a lot of those checks for RD not being 0 should also help as well. Interesting to see how this changes. I think the main lesson here is that like, I'm still generally convinced with this kind of two-process style because, again, I like that really clear separation between the combinational logic and the rest of the logic, and I don't really think that's the issue here. I think the issue here is that I need to get in more of a habit of actually checking the net list when I'm building some of these entities and seeing that things are, more or less how I expect them to be, rather than, being that blind. In the same way that if you were optimizing something on a CPU, you would check disassembly a lot of the time, so it's not really any different there. I just need to get in more of a habit of looking at that. There's a couple things as well where I made some assumptions. Like I fanned some stuff out, assuming that doing the kind of shift that I wanted, particularly in the reads and writes, like the unaligned loads and stores, I did some stuff where instead of having a shift, I just elaborated the cases because I wasn't sure if I did the shift, it's like I need to shift a value by 8 times the number that I have. And I was pretty certain that the compiler wouldn't be able to tell that only like 3 of those bits were relevant, or basically the lower 3 bits were not relevant, I should rather say. So like I could probably simplify the code a lot if I just write it in such a way that it makes it really clear to the compiler that only certain bits are relevant. And the way to determine whether or not the compiler will actually do that is to test it. And so I should test it and gain more experience with that, so that then I can build up an intuition for when that should or shouldn't happen, which will, of course, help me when making these design decisions later. Yeah, the two-process style will definitely rely on the compiler a bit more, which I have no issue with as long as it works. But if it does some nasty stuff, then that's what we're stuck with. Yeah, this is taking a long time to load again, so that was consistent. Yeah, so I think that's an improvement. That's actually really cool to see the difference there. So this was just by removing all those -1s and just having that 0 register be part of our register file. You can even see like some of the fan out here, like in this area here, is basically the same stuff that was here, and you can just see how much more significant it is in the right one, and that's because there's less stuff around it. So that's pretty cool. Oh, that's brutal, 286 tech. But yeah, so I think we can safely get stash pop. Feel good about it. Of course, I have this QSF thing that sucks. Here's what I'll do for this. I'll remove it. That should work. This is annoying that the only difference here is these lines are swapped in that QSF file. So I just get rid of that thing. Yeah. So this is noticeably simpler. I'm still not convinced that that's simpler in the read buffers case, because there is something to be said for trying to be really consistent when using a style like this, and I think I'm not yet ready to commit to not using it, even in some places, because it just means some things are different depending on where you're looking at the code. So I got to think more about that and see more examples of both. But for now, I definitely want to commit this CPU thing. I don't mind committing this stuff in baby steps. Yeah, I also like how this two-process style works, or it looks. That's why I want to kind of keep using it. I do think, though, that if I rename this next to comb or something, that might even make it clearer. But yeah, that's minor detail. I mean, the most important thing is that the code works, that it generates the logic that we actually want it to generate. The second most important thing is that it's readable and maintainable. And I would say that that's a very close second, but that does need to come second. And then third is that it's optimal logic, which is pretty far down by those. Yeah, exactly, Mr. Anderson. Because you could just do everything in like this one sequential process. So it's in VHDL, these always blocks, they're called processes. So I think that's where that name comes from. Anyway, you could just do everything here and then just have, some conditional stuff here, and that would sort of be the same as writing it in one process. Whereas this sort of clearly separates the two. That's all that really is. So that was the most trivial change we could make for this register file. I'm wondering if I should. I think I do want to refactor these writes the other way, because there's not that many places to change them. It's all in this one state. So the way we do this is something like this. We'll do something like logic reg write enable. So basically the same pattern we had here. Or not really, because we're gonna have them as separate signals here, because I still want to have the output of these signals determined by the combinational logic. I just want they just need to be separate, and we're not going to have these and then their next counterparts, because these are only going to be combinational signals. So that's another reason why like renaming all the next ones to comb might actually make more sense, because then like these signals that are only combinational still fit within that logic, and then it's just okay that in the style that I'm writing this, that I have some comb signals that don't also have non-combinational parts, because it would just kind of separate those. But at the same time, that gets back to that whole Hungarian notation in like Windows code, where everything is prefixed based on what it is, and nobody likes that. So we could do like write enable, reg write address. And then this one, of course, is going to be 5 bits to cover the entire 32 bits here. And then reg write value. And again, these can be purely combinational signals. So the way to do this then, also we'll remove regs next just to make sure we don't actually have that. So if we go down to where reg next was, we can do this. By default, these will be 0. And what do we have? Adder and value. Just make it a 5-bit 0. We don't necessarily need to make this one have a default value, actually. We just really don't want this to become a latch. So I'm going to make it have a default value just to avoid that. Because I do actually think that if we didn't do that, that would actually be inferred as a latch. Anyway. So a lot of these just become... Actually, is this address ever not RD? We just look at regs next here. It's always RD. So we don't really need the address. Because we can always just pull that off of RD. The value is going to change, so we do want that, and then the enable is most of the time not going to be anything, but it's going to be something in a lot of cases here on the write back. Not all the cases, because there are some cases where like we write to the PC only. There's a lot of, like stores, for example, don't write back to any of the registers, so it doesn't make sense to do that. So yeah, so then we don't have to do any of these RD checks here already. Another thing here that we can do, so in these cases we know that it's going to be, our write enable is going to be 1, and then our value is what we have here instead of these. There's going to be a similar transform here with these loads. So I think we're already going to have a benefit with this logic, just the fact that we're separating this out the way we are. I think this will become smaller. Of course, we have to add the sequential logic that actually changes this, but we'll get there. All this, of course, is also going to be simpler later, but we'll get to that in a separate pass. The other thing I'm totally going to do is I'm going to get a screenshot of... Oh, actually, I should have done it before changing this because we had that other screenshot. Maybe I still have that. Don't think I do. No, I don't. I'll get that back before we recompile this because I want to do before and after like visual comparisons at every step we do here because I think that'll be nice. Same stuff here. Yeah, so this is a branch, so we're still going to do this like this, and that's fine, because PC Next is not that bad. At least not compared to what we're doing for the registers every time. So here, basically all these cases. Yeah, all 4 of these. So, or all 3 of these. All these guys. And then we'll hit these up. You know what we can also do? Let's call this RD right value. Or RD right enable and RD right value. Just to make that more clear. Because it will always write based on RD. Because then here's what we can do. Instead of having regs next here, we'll do this. If RD write enable and RD is not 0, because this is where we actually still need to do that check to make sure we don't actually overwrite it. Then here, it should be regs RD is RD write value. Now, before I do this, I'm going to remove this QSF file again. I need to see if I just can git ignore that file. But for now, wait, what? Did I just remove that? No, it didn't work. Oh, it said I deleted it. That's actually bad. That's not the one I wanted to delete. I wanted to check it out, not delete it. Yeah, that's fine. Okay. So I'm just going to do another git stash. It stashes the read buffer thing too, and that's fine. And then before we move on, I'm just going to rebuild this again. Now, the annoying part about doing this is these cycles are still pretty slow, but the nice part is that we can basically write everything in the simulator, which is what I did for all these things initially. Is I just did all of it in the simulator. It just worked on hardware, which is awesome. So you could have sort of that faster iteration time when doing that, and then the slower iteration time when doing the optimization, which is, I think, not the worst workflow. Because it also, we only have to wait for this analysis and synthesis part. We don't have to wait for all of the like place and route and everything. We don't have to actually send it to the actual hardware. We're still going to want to test at the end of all this because we need to make sure we didn't break anything, but yeah. Also, I totally wrote a lot of this without regression tests, which if I were doing this professionally, I never would have done. I tend to be pretty strict about that at work, for example. But just as a little side project like this, I think that's fine. It may bite us in the ass later where I'll have to go back and fix bugs. In fact, I'm somewhat certain there's going to be at least one bug in here. That's very, very unlikely that there wouldn't be. But at the same time, I don't think it's going to be that terrible. And I think that someone pointed out that there's a couple like test suites and some verification tools for risc-v cores that I should be able to hook into, and that would be, you know, very nice to just be able to take something off the shelf to verify that the core is correct. Again, another advantage of using an off-the-shelf CPU architecture. Yeah, exactly. 286 tech. Because then we could at least, you know, prove it's correct and also not have to write the tests, which is ideal. That's what you want to do. So seems like we'll get away with it. Again, using risc-v has just been such a good choice for this project. I'm still happy I'm doing the core myself because I get to learn how to do that. And it's a great first core to make, but it's just like we get to tap into all this other stuff around that core, you know, as part of that ecosystem, which is just really, really nice. So here I want to go back into that netlist viewer. So again, this is before. This is it's not our original before, which I also want to do a final comparison at the end of this, but this is the before the change we just made. Yeah, so again, that was a lot faster. And yeah, I'm not digging too much into the details here. I mean, it's just these big old muxes. But as we see this getting simpler, That's good enough for me. Anyway, we're going to do our get stash pop now. And here, I'm also going to just check out this again. Yeah, so this is the pass that basically eliminates all those not equal to zeros. So first thing I'm going to do, by the way, is I'm going to test that it still works the same in the, at least with this, you know, I'm only testing a very small subset of this whenever I do make test, but it should help. Still better than nothing. Output on the command line looks the same, and this all looks the same too. Nothing shifted around, which is kind of the most important thing. I'm also going to add another signal here because we're using risc-v in the test, so we should see that change over time too. So that's all looking good, and then we're going to do this again. And our visual comparison should, again, reveal something that's a bit simpler, just because those comparisons to zero shouldn't be there anymore. And also the, I actually expect that this will reduce a lot of the fan out that we see. Also, I might be using the term fan out wrong. So I'm not a professional. I'm just a guy who likes this stuff and is enjoying learning it. Although after going through this experience, I can say that this might actually be something that I would enjoy doing professionally. I understand, of course, the scale of those kind of projects is, you know, grows a lot. But as with software, I imagine that's a lot of, you know. Oh, by the way, this logic element count seemed to have gone down a lot. That seems to bounce around a bit. I don't know if that's the heuristics just being weird or what, but anyway. Probably, oh, whoa, whoa. That's awesome. Let's check out that before and after. Oh, baby. That was surprising. But I guess that makes some sense. I'm guessing what we have here. Now this netlist looks simple enough to actually look at this. I'm guessing this stuff here, this is our register file, this stuff up here. And I'm guessing a lot of this ends up being like enables on this. So it probably realized that like there's a port on here, which is whether or not stuff is enabled. A bit hard to tell here what a lot of this is connected to. Some of this looks like it's, yeah, so here's write value, which looks like it's, yeah. So I think here's our register file that feeds back into here, and here's this mux over all those registers, which is whether or not the read is enabled. It's going to take either the other value or the new value, which is probably the, yeah, so here's the outputs of these coming back here. And I don't know where a lot of those inputs are coming from. They're gonna feed back from somewhere, or maybe just feed forward from all this stuff rather. Looks like, so here's the right value. Yeah, so here's the value. So the value gets all gathered up here and then muxed here on all the registers. So this is definitely more what we wanted. I think what we had before with that regs and regs next approach, it just fanned out all of that. And became just these enormous muxes. So this was actually fabulous. So again, thanks again to Per Vogensen who pointed that out, that probably wouldn't have done what we wanted. And here we clearly see this is much more like what we described. I think this looks great for the CPU, first of all. Like, this does not scare me at all. The fact that we can see these individual pieces. In terms of the CPU that I have here, I think this is great. I think we can still make some further improvements by simplifying the loads and stores, like simplifying that logic especially. That would sort of be the next, I don't know the term I was going to say. like the next biggest gains, I think, would come from there in terms of simplifying this logic. You're right, Mad Moose. Is it just Voinson? I don't actually know. But I actually don't think that he's Norwegian. At least he doesn't sound Norwegian in his videos. Clearly, it's a very Norwegian name, so maybe he just has a really convincing accent. But anyway. Oh, he's Danish. I didn't realize. I'm very pleased with this now. This is so good. This commit message is going to be fun too, by the way. Again, I just am going to not overwrite this QSF because nothing has actually changed here. Just reordered some things, so I don't give a shit about that. Reduce net list or fix net list explosion. Oh, every time. Can't use bangs. We'll do this. I want those bangs in there. I guess I could use a block RAM for that. I could also separate out the register file if I wanted to do that, and just sort of inject it here as well. Since we are, I mean, I think we do only read from it in one state and write from it in another state. I think we're fine there. This of course here, this is the state itself. It seems to have a lot of different inputs. But I know why it has a lot of different inputs, because there's a lot of states that will transition to transition to like the error state, for example, based on a lot of different conditions. And I'm guessing all these little fans here, we're basically just seeing a lot of those. In fact, I can prove whether or not that's the case. I'm gonna do the same thing, by the way, where I'm just gonna take this, I'm just gonna snip a new screenshot now, because doing this visual compare is good enough actually for our purposes here. The utilization, by the way, I was gonna answer that. Def param, how's it going, by the way? 7506 logic elements. So this has gone down, I think. Not much. But I actually want to do the whole compilation, because it seemed like if I just did analysis and synthesis, this number was a lot higher than if I let it go through the whole thing. And I wonder if it's doing more aggressive optimization later in this chain. So I'm actually want to run this whole thing just to see if that actually changes. How's it going, Niner Delta? Yeah, this really isn't too bad. I mean, it's just the CPU core, the memory mapper, the LED interface, and the ROM. It doesn't have the DDR3 controller, which is another 6K or so, as far as I remember. But also that's not bad at all. Like we're under 15 out of 50, getting most of the parts in place. And if we have the rest of that basically for the GPU and the audio unit, then we can do a lot of parallelism. So that's actually really cool. Although we'll see if that actually makes any sense, because I think we're going to be IO bound on a lot of this stuff anyway. If I make it programmable, it'll make a lot of sense. But if I make it just like flat shaded polygons, for example, then IO is going to be our biggest pain there. But then maybe some vector processing in the CPU or something could make some sense. Could also do just like a really basic vector processor of my own design that might even just do integer stuff. That could be kind of fun. We'll have to see. I don't really know. I also was looking at it. So currently, my plan is to do the video output resolution is going to be 640 by 480 at 60 hertz. I'm thinking I might do 320 by 240. We'll have to just see what the performance is like, because that's a quarter of the video bandwidth I have just for output, and also quarter of the amount of pixels to actually write. Plus, a lot of the consoles of the era that I'm trying to create this for use that resolution still. FPU, of course, would be awesome to have. I'm kind of trying to avoid it because I don't want to do I don't want to implement IEEE. That just doesn't seem very fun. Although I think it would have a lot of gains, of course. Otherwise, we're doing soft float. Soft float on a CPU that is not pipelined. Yeah, so now we're at 4503 registers. That's still the same, which makes sense because we haven't reduced any state. We just simplified the signal. So we saved 1,000 logic elements by doing this change. That's pretty sick. Yeah, that's exactly it. Integer multiply and divide I'll probably do, because I don't think those will be nearly as complicated. And I mean, even doing like a naive approach to either of those is still going to be faster than, like if I just take some software algorithm and just port it, then it's still going to be faster and more useful than not having it. So I think that'll be relatively straightforward. Again, I think if we do the netlist viewer, I think it's going to look the same. This is so cool though, just to see this thing take shape over time. Yeah, this is no different from what I can tell. Let's see the two side by side. Yeah, built-in AES is exactly what the system needs. Oh, this is super motivating though, just to see this change shape. I love here's the ALU. We have just these clocked registers for the. Yeah, so here I think these are the registers too, because again you have these clock enable bits, or clock and enable inputs, and the Qs are the outputs. So I guess that's a lot of what's happening here at this register file too, is these are the different registers themselves. Yeah, so here's register 25, all 32 bits of it. Here you can see the fan out of the different bits, but these are the actual registers themselves. And then again, I think these enable signals end up getting tied down here. To write enable here. So there you go. I think that's mainly why this got simplified. I totally might do that, Mad Moose. Even if it's integer shaders. Oh, this is really cool to see the difference here. What a very useful 2 hours to have recorded. I'm really happy I did this on stream today. Like I think having this on stream is actually more valuable than the original process I used to write this logic, because I kind of just threw it all together. Like I was looking at the spec and just kind of wrote it, and it was really straightforward due to the way that risc-v is encoded. So I'm just really satisfied. And it's so much faster to go between these netlist views too. Okay, so the question is, I've been streaming for 2 hours now. And the real question is, do I want to tackle these loads and stores now or not? And I'm kind of thinking not, to be honest. Because I need to not get to work at 12 tomorrow. So I think I might head out. The process for that is basically going to be the same, and I'll go over it on whatever I end up with. I'll go over on the next stream anyway. So I think I'll probably call it quits here today. I think that's a good idea. Again, I want to thank Per Vogensen again, just because again it was him. Like I just posted the fact that I had this CPU working yesterday, and then I woke up this morning to like 13 tweets. just about like things that could be improved, and a lot of this. So this is pretty cool. Oh, I totally will diff param, because I just ran the whole compilation, didn't I? Yeah, nice. I'll totally do that. Here we go. Here's our chip planner output. Whoops, I don't know what I clicked on. Zoom. It's laid out all over the place. I mean, just as well, I guess, because it's not like... I think this is basically only tied to the LEDs for the output, and then it's going to be using some memory for the ROM. So I mean, it's just as well that this is anywhere. Of course, when you have the DDR controller, it's all going to be over here on this right side, but that's not in the Xenowing project yet, just in the DDR test project. Because that's still one of the things I have to do next, is hook up all this stuff to the actual memory. But yeah, I'm still so happy with this project. It's going so well, realistically. I mean, I did spend a couple weeks just sitting there wrapping my head around, you know, the DDR3 controller and getting all that to work. But at the same time, that gave me a lot of experience just navigating through these tools. And even the small subset of these tools that I understand so far has been useful enough. So this is actually pretty rad. So I think we saved like 2% of our logic units. But actually, so I'm just going to do this really quick before I go. That's going to be the same as 6733. So if we do 6733 divided by, not the program one, we need the scientific one. 6733 divided by 7797. 1 minus 0.86. So that's a 14% reduction in the logic, just by rewriting a couple things. And obviously the netlist looks a lot better, and I can actually navigate this nicely, which is cool. Yeah, I mean, to be fair, also Defram, like I did fight a lot with this stuff a couple years ago. And at least I have a lot of software experience, which really carries over in terms of like knowing which kinds of things you can simulate and which kinds of things you can't, and understanding the value of just simulation and mocking in those kind of environments, I think really helps. So I think I picked up a lot of it from there. But at the same time, I am also pretty happy about this. Danny Fritz, there is a limit to the logic elements. It's about 50,000 on my chip, so we have plenty of headroom. Considering this and then the DDR3 controller are about the same size right now. So around like 13,000 or something. 14,000 out of 50. So we got plenty of space. There is going to be some more that is taken up, of course, by more of the memory mapping as that gets fleshed out and is actually able to touch the DDR3 and all the interconnect that goes with that. But I don't expect it to be too bad. Yeah, we have all the stuff from the read buffer as well, too, which all comes in here. Still lots of muxes. But yeah, the biggest thing here, I think the difference is, you know, a lot of these are still 32-bit buses that you see here, 32-bit wide signals, but the fact that it's able to lay it out this nicely, I think it just shows how much of the logic has now been collapsed, which is, I think, the important thing here. Yeah, the last thing I'm going to do, by the way, I think I'm going to remove some of these default cases that just go to error states because I don't need them, and they don't actually help. I only put them in there to shut up the compilers about the fact that I have some cases with incomplete lists. So I want it on this top level one because, like, on startup, this would take us to error state if it wasn't reset properly. Misaligned PC, I want to keep that. Stuff like this where I get a system instruction that's one of these, we actually couldn't have gotten to this state without having one of these. This one we could have if we tried to read like a random one that was wrong. Again, here we couldn't have gotten to this state without already having decoded this value for which kind of load it is. Let's see. Yeah, for the loads and stores, we definitely already know, like we've already decoded these once in the previous state, so there's just no reason to have these here. Again, same here. I just have a lot of these in here. Yeah, these load weights, we don't need them there. Don't need this here. Don't need this here. Okay, yeah, so even here, we even checked this value already here, so I think I can even remove that down here. No, that's not true, because I don't check the addresses until I get here, so we actually do want that there. So that's correct. Also, I didn't remove... There's some more of these I missed. This one. This one. Don't need those at all. We'll keep these ones because these are like decoding errors. Yeah, like the branch, these need to be valid. We could also not do that and just see what happens. That's how you get that's how you get undefined opcodes. Which is probably fine. So I'm just a bit curious to see if this shrinks. Do I still have a screenshot here? I don't think I do, but I want one. I'm gonna run this here first because our simulator is a lot faster. Yeah, so now we get all these case values incompletely covered. I actually don't really know how to suppress those in a lot of these cases. I might just convert them to ifs, just because it's more explicit that I only care about certain cases. And that would be a good way to shut it up in all compilers because we're using 2 compilers here. And I'll probably switch to using 3 because I'm thinking about using Icarus Verilog to do linting as well. Because I apparently it's more pedantic than some other ones. So, and the more compilers you can put the logic through, the better it is, and just in terms of finding errors because there's some overlap in their features. Anyway, this looks okay, and then this should stay the same. Whoops. Control-Shift-R. Yep, it does. And we'll just run this through compilation again. So all I'm predicting here is that the inputs to this state thing just shrink up because there's not going to be nearly as many conditions that take us to an error state anymore. And generally I don't want to have a lot of those like extra decoding checks in anything other than the decode state. The software I'm using for the waveforms, Mr. Anderson, that's just GTK wave. You can see the logo up here, GTK wave. It's super standard for this stuff. Yeah, exactly, Defram. I like Verilog, but much like C or C++, the compiler's only going to do you so many favors in terms of making sure you're doing the right thing, which is fine. Practically speaking, it's only a problem if I'm really bad at this. I'm not ready to admit that I'm really bad at this yet. I'm inexperienced, certainly, but we have yet to see if I'm really bad or not. I'll probably do the load and store simplification off the stream just because I'll probably do it in the next couple of days. But if I don't get a chance to work on this stuff again until Saturday, which might be somewhat likely actually do the rest of my plans this week, then we'll see it on the stream. What does that do, 286 Tech? Oh, also, I'm totally going to run this in Signal Tap again. We should see basically exactly the same signals, except I think these ones will change because I only tap register 0, 1, and 2, and now these are offset. So this is currently register 1, 2, and 3, but now these will change. Other than that, this should actually be identical. But that's the other thing, is that the utilization that I'm showing here is also with Signal Tap. Yeah, we saw exactly the right things change. That's great. So this may actually be a little bit different with, like, of course, it's going to use a little bit less when you don't have that enabled. So here, just going to the CPU again. Whoops, why am I getting just the register there? So here's the before and after now. It does actually look simpler. Not that visibly, but I'm pretty well convinced. Actually, you can see a lot of thickness down here, which probably just means more logic too, versus this. Yeah, actually when you look at a lot of the combinational stuff here, the left is definitely simpler. Or at least things got pushed around a bit. I think it looks simpler. So I'll probably stick with that change too. Other thing too, I'll just check really quick. 6714. Yeah, so a few less logic units. Should be the same amount of registers. Now we're 13% rather than 14. It's kind of neat. So it'll be interesting to see again how this is improved once we refactor the loads and stores a bit. I'm still, as I said before, I'm still probably gonna do the loads, the unaligned loads and stores in hardware, just because then I don't have to figure out how traps work, which I'll still probably want later. But then at that point, I can make that change. So I'll have to say screw it for now and just improve the logic that I have, which I know I can do, and then worry about traps and stuff later. What are implicit or implied nets? I don't know what that means. I love this. Look how simple our ALU inputs and outputs are. That makes me happy. I'm really pleased with this. I think this looks great for a CPU. Lem T, thanks for the follow. Ah, gotcha. Yeah, that sounds brutal. I haven't really had the issue that I've forgotten that yet. I think. Maybe I have and didn't know about it. I guess that's the issue. I'll definitely have to add that. Anyway, I think I'm going to head out now. I'll leave you with this beautiful picture here. Check it out. How cool the CPU looks. Look at all that logic up there. Yeah, I think the typos are definitely where that's going to happen. Anyway, thanks guys for hanging out. Thanks for the tips. Thanks for the help. This was really fun. I'm really happy to have done this on stream and recorded this as well. And I'll see you next time, probably on Saturday.